Hey, this is Mr. Mitchell with another video. This one's about Newton's second law of motion. But before we talk about that, write the questions and let's talk about the lunchroom. Imagine sitting at the lunchroom table. Well, let's say you're right here. Put your hand on your milk. You're a little bit short there. Your friend way down here says, "Hey, can you pass me the milk?" You take the milk and slide it all the way across, because I'm sure nobody's plates would be there. What if he had asked for a gallon of milk? You could not use the same force that you used in sliding this little carton of milk over that you would if you were to send this gallon of milk over. You would have to apply different forces. And Newton's second law actually applies to this kind of scenario. The acceleration of an object, in this case, carton of milk or jug of milk, the acceleration of an object depends on its mass, as you can see the difference here, and the size of force applied to it. And it is summed up in the equation force equals mass times acceleration. So here we are at the lunchroom table. You have a small amount of mass. So you have to apply not much force to get it over here, to accelerate it over. So let's see what I have in my notes here. Force equals mass times acceleration means three things. The first thing it means that the bigger mass is going to require a bigger force to achieve the same acceleration. Another thing it means is if you increase the force on equal masses, you increase the acceleration. Say you had two of these little cartons instead of one carton and one jug. To get one to go faster, you would have to increase the force that you had on it for one to go faster than the other. And a third thing that it means is that if you use equal masses, if you use the same force on two different masses, the acceleration decreases with mass. So the acceleration decreases whenever you have a large thing here. It's not going to be able to go as far if you use the same amount of force. So it's something that is kind of common sense, but nobody before Newton had really been able to put it to a formula. And of course it means a little bit more than just a simple, hey, it's harder to push a gallon than it is a carton. To use this formula, you need to understand the unit of force. Mass is going to be in kilograms. That's the standard scientific unit. If it's not in kilograms, you can change it to kilograms. Acceleration, you may remember, is meters per second squared. Now, you may remember acceleration is going to be meters per second over second, which is meters per second squared. You know, we calculated that in the last video. So force is a term that is kilograms times meters per second squared. And instead of having to write that, people generally use the term Newton. So whenever you start calculating these forces, it'll be so and so number of newtons instead of such and such number of kilograms times meters per second squared, which is a good thing, I suppose. But anyway, what if you were given the force, given the acceleration, and not given the mass? I think I touched on this on the last video, but not the last video, but one of the earlier videos, but I was running out of time. You can actually solve for a certain one of these. Let's show you how to solve for mass. If you have everything but mass, you have to isolate mass on one side. So to do that, you divide both sides of the equal sign. You have to do the same thing to each side. So let's see, how can we get rid of this A? You divide by it. That's how you can get rid of that A. So that means mass equals F over A. Mass equals force over acceleration. So you have to get rid of the A, and to do that you divide it by A, which is something you have to do with both sides. It's kind of a short, sweet, and simple way to do that. And I know we haven't done that in this particular class, but you'll actually need that for something later on. Actually, it'll be some of the calculations which we have here. So we have force equals mass times acceleration, and we have solved for acceleration. I think this one down here is going to be using this formula, and you saw how we got that. So let's try this one. A man hits a golf ball, which is weighing 0.2 kilograms. It accelerates at this rate. So we have the kilograms, we have the meters per second squared. We're asking for force. Hey, that should be simple. Force equals mass times acceleration. Mass is 0.2 kilograms. And acceleration is 20 meters per second square. So in this case, it is just a matter of multiplying 20 times 0.2, which I think I'll just do up here because it's not too much. 4.0. So you have 4.0 newtons. Don't forget, you get to use newtons here. Hey, that's a good thing. What's the acceleration of 10 kilogram mass pushed by a 5 Newton force? Let's use this one up here. Acceleration equals force over mass. And force is in newtons, so that would be 5 newtons over 10 kilograms. So 5 over 10 is 1/2, which is 0.5, and acceleration is in meters per second squared. So that's a couple of ways of how you would go about doing that. Let's talk about centripetal force. What about objects moving in a circle? Multiple forces are certainly going to be at work here. Now, Newton's second law stipulates that the object accelerates in the same direction as force. So an object, let me get that all here, an object changing direction has a force propelling the object in the other direction. So say this object is going this way, that's typically what Newton's second law is talking about. That the acceleration and the mass and the force are all dependent upon it having just one force upon it. But if you have something going in a circle, like this bucket here that this lady is spinning, like this skater here that this little guy is spinning, you have more than one force upon it. But some parts of Newton's second law do still apply. Like an object's tendency to stay in line, objects in a circular motion tend to have a force that keeps it moving in a circle. The force that keeps it moving in a circle is called centripetal force. And you can see here, this is the centripetal force pulling the object out of a straight line of path. And here the centripetal force is going to be the rope. The rope is keeping this from flying off. This guy's hand is going to be this arm is going to be the centripetal force, keeps this girl from a nasty accident flying toward the wall. That is the centripetal force. It keeps the objects moving in a circle. Now, of course, if she lets go, this bucket is going to go flying in a line. If he lets go, she's going to go flying in a line. But the centripetal force keeps them in a circle, going around and around in a circle. When whirling something in a circle, you must pull harder, the faster it goes. So as she twirls this bucket harder, she'll have to have more force to hold on to it. The faster she twirls, his arm's going to get tired because he's having to hold on to it harder. And that's just kind of one of the ways it has to do with the centripetal force. Now, how does this apply to Newton's second law? Well, with more than one force, it's going to be a different formula. We're not going to cover that particular formula in this class, but the overall principle still applies. The greater the mass, the greater the force needed to accelerate. So we had said that acceleration, if we change the formula to solve for acceleration, we have this. That's Newton's second law. Different formula here, but the same principle applies. The larger the mass, the bigger this number. To keep up acceleration, you have to have a bigger this number. What if I move this number? I'm just going to throw some numbers in here. What if I make this number 10? You have to have a bigger acceleration, this number has to be bigger. If I just put 1, that's very small. But if I put 100, that is much more acceleration. So you can see that to have a larger mass that you're twirling around, you have a larger force that is holding on to it. Same thing here. You have to have more force here. Have to have more force here to keep them going faster and faster. The more acceleration you have, the more need you have for force. Well, I hope you've learned a little bit about Newton's second law.